trigonometry, you end up using cosine again. But you can use the cheat method. To get from what I'm given to what I want, do I cross a known angle? Yes, I do. Well, then I'll use cos. So the horizontal component of the velocity along this desired horizontal axis is 60 cos 40, and you put that in there. Vertically, because vertical motion is experiencing the acceleration due to gravity, then we are not allowed to use d equals vt. We have to use the constant acceleration equations. Now at higher, there's 4 constant acceleration equations: v equals u plus at, s equals half u plus v times t, v squared equals u squared plus 2is, and s equals ut plus half at squared. Which one you use, again, depends on your shopping list. This is why shopping lists, you need to use shopping lists. So just some top tips to remember when using this. If you're dealing with everything in the vertical axis, then you have to have the starting speed in the vertical axis. So the starting speed at the moment is not in the vertical axis, so take that starting speed, turn it to the vertical axis that you want. Now as you're rotating it to get to the vertical axis you want, you are crossing an unknown angle. So if we cross an unknown angle, then we use sine. So it's the initial speed in the axis we want is 60 sine 40. Again, if you wanted to do a triangle, then you could use triangle trigonometry rather than that cheat method. So anyway, you've got u, so vertically u is 60 times 40, and then wherever you see u, you could put that in there. A, the acceleration due to gravity, is always going to be 9.8 meters per second squared at any point in which this thing is moving unsupported. In other words, it's not hitting the ground, it's not bouncing. Be very clear on which direction is positive. You might take upwards to be positive, you might take downwards to be positive. If you take upwards to be positive and the thing is doing this, then okay, u is going to be positive. So we're talking about vertical stuff, then u is going to be positive 60 sine 40. But if upwards is a positive direction, then a is going to be negative 9.8, and you're going to have to remember to make a negative in your formulas. If you are dropping something, then it would probably make sense to say that downwards is the positive direction, in which case a in these situations would be positive 9.8. So don't just blindly say, well, a is always negative 9.8. It depends on which direction you're taking as positive. If something's lobbed up forwards, but you're just thinking about the vertical situation, at the top of the flight, vertically, although the ball will still have horizontal motion, vertically, for an instant or less than an instant, it will be at rest. So you can say at the top of the flight, then v, the final speed, is 0. So you could stick v equals 0 in, and that would allow you to calculate stuff. The total flight time of something chucked up is 2 times the time it takes to get to the top, because it's a symmetrical flight path, because we're not dealing with air resistance. Interpreting motion time graphs. Motion time graphs and interpreting them and working out what goes on and what they're showing, it's quite good fun if you're kind of approaching it with a sort of mindset of a Sudoku or whatever, or a crossword. Unfortunately, that's not the mindset which you find yourself in when you're doing a physics exam. So I suppose I appreciate that. But I suppose my best advice here is try and picture in your mind what is going on. The graph is not a picture. I mean, it looks like a picture, but it's not a picture. The graph is data for your own mental picture. Use some imagination and think in your head about what's going on. Get a mental picture. Also think about key moments. So let's just do some examples, shall we? So let's say we've got a ball trundling along horizontal at steady speed, and then it goes down a ramp or whatever. Here's the speed time graph, the velocity time graph. it's trundling along at a steady speed, and then it starts speeding up as it goes down the slope. What about the acceleration time graph? Well, if something's going at steady speed, it's not accelerating. Well, there's zero acceleration, and then it hits this point, and all of a sudden it accelerates. It starts speeding up. So all of a sudden we've got a steady acceleration. We know it's a steady horizontal acceleration because the speed is speeding up steadily. So if something's increasing speed steadily, the influence, remember acceleration is quite useful to think of acceleration as an influence, the influence must be steady. At Nat 5 we only ever really dealt with speed time graphs. At higher we've got the acceleration time graphs and the displacement time graphs. So here's sort of your Nat 5 standard speed time graph. Here's a car accelerating, then it goes at steady speed, and then it decelerates, maybe at a slower rate than it accelerated. So this, you've got a steady increase in speed, so there must be a steady influence. Here we've got no change in speed, so there's no influence. And here we've got a reduction in speed, so we've got a negative influence. Because this is happening over a longer period of time, then the negative influence, the negative steady influence, is not as big as the positive influence. Let's say a ball is thrown up, it comes back down, it's caught when it comes back down into the hand. So very simple, hand, throw it up and catch it when it comes back down. So to remember what we're saying about key moments, you think to yourself, well, when it leaves the hand, it's going quite fast, but it's going in a positive direction. Let's take upwards as being positive. Over time it goes up, but then it slows down, and at the top of the flight, for less than an instant, it is at zero speed. And then as it comes back down, it speeds up, but it's speeding up in the downwards direction, which is negative. So this is when a ball is thrown up and then it's caught at the bottom of its flight. And just before it hits your hand again, it's going fast, but it's going fast in a negative direction. So this is what we mean about thinking about the key points. Key point. The area underneath a speed time graph is the displacement. So this coloured in area here is the distance going from your hand up to the top, and this area here is the distance from the top down to your hand, and the displacement, which if you remember is the very start point to the very finish point, is 0. So this would be a positive number, this would be a negative number, and it would cancel out to be 0. An acceleration time graph would just be steady negative 9.8 meters per second squared. This is the gradient of the speed time graph, or the velocity time graph, and remember we said anything moving unsupported in the gravity field on Earth will experience a downwards acceleration, which in this case is negative, of 9.8 meters per second squared. This isn't bouncing at all, it isn't hitting anything. As soon as it's left the person's hand, it's moving unsupported in the gravity field, so anything moving unsupported has this steady, constant 9.8 meters per second squared influence on it. This is an interesting example, I quite like this one. A swimmer going out and back. So they jump in, they go out and they go back. So 2 lengths of a pool in total. So if you're just thinking about the distance you're going, distance time, then distance doesn't really care about direction, does it? Are you just, I don't know, is it 30-meter pool is standard? So you keep on going, and I suppose this would be 60 meters up there, and you've covered that distance. A displacement time graph, everything is with respect to the origin or the starting point. So you go up, this point would be 30, and it would be halfway through, and then you'd actually start coming down, you come back to your starting point, and overall, the overall displacement would be 0, because the starting point is the same as the finishing point, so the final displacement is 0, and this would be 30, whereas this would be 60. Here we have a ball which is dropped, and it bounces twice, and then it's caught. So here's a speed time graph, a velocity time graph, and again think about key points. So if we're taking downwards as negative, upwards as positive, then when it leaves the person's hand, it rests initially, but then it speeds up in the negative direction, speeds up, and then it hits the ground, and then a very short time later it leaves the ground going quite fast in the positive direction. So this is what we mean by a key point. Here's a key point. So in a very short amount of time it changes from being downwards quite fast, or downwards very fast, to upwards quite fast. And then it leaves the ground, and as it goes up, although it starts going up quite fast, it slows down. At the top of the flight it's at rest, and then it starts speeding up in the negative direction. It hits the ground again, and then it leaves the ground as a fastish speed, and then it's on the way up, it slows down, and at its highest point it's caught. So what would the acceleration time graph be? Well, any of the time it's not being supported by the ground, it has a constant negative 9.8 meters per second squared. At those points it is being supported by the ground, in other words, the duration of the bounce, it has a positive acceleration or positive influence. Let's think about a ball which is thrown up. It comes down, it passes the person's hand, maybe they miss it, they don't catch it, it goes down to the ground, it bounces, and it caught when it's come back up to its highest point again. So here we go. Think about the key points, speed time graph. The ball leaves the person's hand with, let's say upwards is positive, with a fast positive speed. But then as it goes up, it slows down. This is the point of its highest flight. Then it starts speeding up in the opposite direction. It goes past the person's hand and keeps on going down, faster and faster. It hits the ground. Very short amount of time later, it leaves the ground going reasonably quickly in the positive direction, and then as it goes up it slows down, and then this is its highest point where it's caught. Again, throughout all its unsupported flight, it has a negative 9.8 meters per second squared influence, negative acceleration on it, apart from the time it is supported when it's bouncing on the floor. Here we have a Lancaster bomber dropping a bouncing bomb. So let's think about a speed time graph or a velocity time graph. It's going to steadily increase its speed. Now notice in this case, because everything's going down the way, we've said, well, let's let down the way be the positive direction. So it's increasing its speed. Its speed's going up, so there's clearly a positive acceleration going on. If we get the gradient of that, we'll find that positive acceleration, but we know what that's going to be. It's going to be positive 9.8 meters per second squared. It's a positive influence. This thing is speeding up in a positive direction, therefore there's going to be a positive influence. And it's unsupported, so we know it's going to be 9.8. Yep, now that's positive. Alright, now think about displacement time graph. As it's accelerating, the bomb is going to start moving away from it slowly, but then it's going to move away faster and faster. So a displacement time graph would have this curve to it. Best way to think about displacement time graphs is literally think about you standing at a point, an origin in a room, I don't know, next to a desk or whatever, and then moving away from it. And so if you start accelerating away from it, then think about the distance from that desk. Then it kind of makes sense. The distance from your desk starts out reasonably small, and then every second, because you're accelerating, you get a greater and greater distance away from the desk. It's not a steady increase in displacement from the desk. It's an increasing increase, if you like, in distance from the desk, which is why it's a curve. So you do have to think about displacement time graphs sometimes. And top tip for displacement time graphs, think you're standing next to a teacher's desk or whatever and moving away from it, and think about how you're moving away from it. Oh my word, more of these graphs. I think this is the last one. A bouncy ball is dropped. It bounces, it comes back up to the same height. Downwards is the negative direction. So it leaves the hand 0 speed, and then it speeds up in the negative direction. It hits the ground, leaves the ground to the positive direction. As it goes up, it slows down. Speed time graph or velocity time graph. Acceleration time graph, that's the point when it's supported. Throughout the rest of the flight, when it's unsupported, you have a negative influence, negative 9.8 meters per second squared. This is the displacement time graph. So when you drop a ball, it's going 0, and then it's gradually speeding up. So the displacement, again, you can think of it as somebody moving away from a desk in school. They start at 0, and then they're gradually speeding up